Good afternoon, everyone. Professor Jean-Michel Coron, Mr. Eric Chauvel, Deputy Counsel for Culture, Education and Science, Consul General of France in Hong Kong and Macau, esteemed colleagues, Professor C.S. Lee, friends and fellow students. I am Li Shuai, Associate Vice President, Strategic Research at CTU, and the facilitator for today's lecture. It is my great pleasure to welcome you all to this installment of the France-Hong Kong Distinguished Lecture Series. So before I invite Professor Coron to the stage, may I invite our Provost and Deputy President, Professor C.S. Lee, to deliver the welcoming remarks. Professor Lee, please.
Good afternoon, Professor Coron, Mr. Shehu, ladies and gentlemen. It's my great pleasure to welcome all of you on this special occasion. Today marks another milestone in our long-standing France-Hong Kong Distinguished Lecture Series, a platform that has bridges academic excellence between France and Hong Kong for over 20 years. As the world's most international university for 3 consecutive years, and one of only 2 universities in Hong Kong ranked among the top 100 across 4 major global ranking systems, City University is uniquely positioned to foster resilient, trust-based collaboration that enhance global academic excellence and innovation. This event aligns perfectly with our vision, bringing together minds from across borders to explore cutting-edge ideas in control system and stabilization, topics with profound implications for engineering, environmental management, and beyond. We are honored to host Professor Jean-Michel Coron, an eminent scholar from Sorbonne University and a distinguished member of the French Academy of Science. His contribution to mathematics and control theory have inspired generations, and we look forward to the insight he will share today. I would like to express my heartfelt gratitude to our IAS Senior Fellow, Professor Philippe Chalet, and to the Consulate General of France in Hong Kong, Macau for their immense support since the establishment of this series. Their dedications has been instrumental in sustaining and enriching this meaningful collaboration. Thank you once again for joining us today. Let us continue to build these vital connections that enrich our academic community and contribute to a bright future. Thank you.
Thank you, Professor Lee. Please remain on the stage. Now we're delighted that Professor Lee will present a gift to Professor Coron with a portable tea set on behalf of CTU Hong Kong. The tea set symbolizes the elegance of Chinese culture and our shared commitment to excellence. So please accept this gift as a token of our appreciation. We hope you will enjoy it. Thank you. Next, I would like to invite Mr. Eric Chauvel, Deputy Counsel for Culture, Education and Science, Consul General of France in Hong Kong and Macau, to give the opening speech. Mr. Chauvel, please.
Thank you. Thank you very much. Thank you, Professor Li Jun Xing, dear Professor Charlet, distinguished professors and representatives of City University of Hong Kong, dear Professor Jean-Michel Coron, dear researchers and students, ladies and gentlemen. It's a great pleasure and a true honor for me to represent the Consul General of France in Macau and Hong Kong this afternoon and to join you for this distinguished lecture by Professor Jean-Michel Coron. I had the pleasure of attending a previous one since I've been here in Hong Kong only 2 months arrived in January, so it's not long, but already 2 distinguished lectures in CTU. It's good. It's good rhythmus. I should keep going. Professor Jean-Michel Coron is one of France's leading mathematicians in the field of control theory, and his contributions have influenced generations of researchers around the world, and we are deeply honored to welcome him today. Allow me first also to warmly thank University altogether and the President for hosting us today in this remarkable venue. I would also like to express my sincere gratitude to all those who have contributed to the organization of the event. The Distinguished Lectures series of City University are a vivid illustration of the strong and enduring intellectual dialogue that connects France and Hong Kong. A dialogue built on academic excellence, openness to the world, and a shared conviction in the universal value of knowledge and sciences. First, I'd like to underline the importance of science as a driver of progress, particularly in an always more complex world that can sometimes be an excuse to jeopardize scientific research. Science, the pursuit of truth, and the desire to foster collective progress in knowledge and a better live together in society are intrinsic values and must regain their rightful place as such in our society. France is firmly committed to foster knowledge and research which are essential for developing the innovations of tomorrow, whether scientific, societal, or cultural. As for mathematics, mathematics is referred to as the queen of sciences or the key of sciences because it enters into and governs almost every other department of knowledge. Mathematics, often perceived as abstract, is one of the most powerful tools we possess to understand complexity and to design solutions for the challenges of our modern societies. Professor Jean-Michel Coron's work stands precisely at this intersection between theoretical excellence and real-world applications. Through his pioneering contribution, he has significantly advanced our understanding on how mathematical models can help regulate complex phenomena. We are therefore deeply honored again to welcome you today and to benefit from his insights. Secondly, I wish to underline the importance of defending free and open science. Free and open science lies at the very heart of our societies. The ability to search, to question, to debate, and to challenge ideas through evidence is one of the foundations of our intellectual and political traditions in France and Europe. From the Renaissance to the Enlightenment, Europe was shaped by the belief that knowledge progresses through freedom of inquiry and the open exchange of ideas. Without this freedom, our relationship to truth, to informed public debate, would become fragile. This is why France and Europe remain deeply committed to defending academic freedom and supporting the conditions that allow science to flourish. Through international collaboration, as this one, peer evaluation, and the circulation of knowledge. Third, I would like to stress the importance of strengthening scientific cooperation between France and Hong Kong. Over the years, our cooperation has grown through numerous academic exchanges, research collaborations, and institutional partnerships. Universities and research institutions on both sides have contributed to building a vibrant community of scholars who have shared ideas, expertise, and curiosity. And as I was telling you, I've only been here 2 months, and during API week at the end of February, there were over 50 universities that had sent some representative from France to Hong Kong on this particular event, and this shows the importance of Hong Kong in the map of the scientific and academic world now for us, but also in Europe. These collaborations reflect a shared ambition to foster excellence, to encourage scientific mobility, and to strengthen the bridges between our research communities. I trust that this academic cooperation will continue to grow. The first ever forum between university presidents of France and Hong Kong that will take place this year in Paris on the 21st and 22nd of May is also another opportunity to initiate new joint academic and research programs between France and Hong Kong. On this occasion, France Université and the French Academy of Science would be honored to welcome the president of CTU among the Hong Kong delegation. And I would like to finish my point by with some kind words for our Consul General, Honorable Christine Druhl, who regrets that couldn't attend this gathering today, and is wishing us fruitful exchanging this afternoon. Thank you very much. And vive la coopération entre la France et Hong Kong.
Thank you, Mr. Chauvel. Please remain on the stage. May I invite our distinguished guests, Professor Coron, Professor Charlotte, Professor Lee, Professor Chang, Professor Ho, please up on the stage, take a group photo, please. Thank you. Now I am honored to introduce the speaker today, Professor Jean-Michel Coron, Professor Emeritus at Sorbonne University, will deliver a lecture entitled From Ancient Water Clocks to Modern River Regulation, the Evolution of Control System Stabilization. Professor Coron is a member of the French Academy of Science and the Academia Europaea. His work has earned numerous prestigious awards, including the Fermat Prize, the Douglas Prize, the ICIAM Maxwell Prize, and the WT and Indira Ree Prize from Siam. I don't think you guys are here to listen to me to speak, so I would not waste the precious time of yours here. May I invite Professor Coron on the stage, please?
First, I want to thank Eric Chevreul, Professor Lee, and Professor Lee. But maybe the pronunciation is not the same, I don't know. Thank you for the presentation. I also would like to say that I am very honored to be here with you. I want to thank CTU for giving me the opportunity to be part of this French Hong Kong distinguished lectures. And I also want to congratulate Philippe Ciarlet. Philippe Ciarlet in 2005 has created this wonderful distinguished lectures to connect scientists from France and Hong Kong, and it is very successful, and we are all grateful to him for this famous lecture series. Let's move now to my talk. My talk will be on stabilization, and I will present first I will present the stabilization problem. Then we are going to move to presentation of historical regulators and the historical study. Then I will explain how Lyapunov function can be used in order to stabilize rivers. And finally, I will present you the offset problem, which has been which is very interesting. So the stabilization problem is a very classical problem. You have, for example, a cart which is moving on a line, and above the cart there is an inverted pendulum. So this is a rod with a ball at the end, and there is a center of rotation, C, and of course this equilibrium is not stable. So either the ball is going to fall down on the right, or it's going to fall down on the left. And then the idea is to apply a control force, which is going to depend on some measurements, in such a way that now the equilibrium, which is unstable without the feedback, becomes stable. So here is a double inverted pendulum that you can see at the Museum La Villette in France. So now there is two inverted pendulums with a center of rotation between them. And you see the machine succeeds to stabilize this inverted pendulum. Knowing only two measurements, the machine knows the position of the cart and the angle of the first rod with the verticals. This is something that a human cannot do, but the machine can do it. What we can do is what is doing James Stewart in the movie Vertigo. he has a leg in a cast, and he has on the top of his finger a walk stick. And this equilibrium is unstable, and he's moving the finger in order to stabilize the system. Of course, maybe you are too young to have a walk stick, but you can make it with a broomstick. And you see, he's looking at the top of the walk stick, which is the place where is the best information. Now, some historical regulators. The first one, I think, is the water clock. This is something that which is very old. I think it was invented in China, maybe 3,000 years BCE, under the reign of the emperor, Yellow Emperor, I think. So you want to measure time, and the device is as follows. You have a tank, there is some water inside the tank, and there is a hole at the bottom of the tank. Then the water is draining out, and you can hope to measure the time by measuring the water level inside the tank. Here this is the oldest water clock which reaches. This is coming from Karnak. You see, it's very beautiful. The hole is on the left of the picture. You cannot see it very well. And here is from some clepsydra from China. They were discovered recently. They are very beautiful. But there is a drawback, because as the time is increasing, the water level is decreasing, and then the flow rate is changing. It is decreasing. So the evolution of the time is not proportional to the decrease of the height of the water inside the tank. And to avoid this drawback, Cecibios is supposed to have invented this device. Now we have 3 tanks, and the tank which is interesting for us is tank number 2. There is a float inside the tank, which is in red, and when the height of the water inside tank 2 is large, the float is touching the green part, and no more water can come from tank 1 to tank 2. While if the water level is low, then the float does not prevent anything, and the device is such that there is a little more water coming from tank 1 to tank 2 than going from tank 2 to tank 3. And with this, you may hope to have a level which remains constant in tank 2, and then the flow rate is constant, and then we have the solution, because now the increase of time is just proportional to the increase of the water level inside tank 3. In fact, it's not clear if Cecibios has really invented this device, because the manuscripts on this are not very clear. But here is a manuscript of an inventor which is called Pseudo-Archimedes, who lives in the 3rd century. This is a copy of the 14th century that you can see at the Bibliothèque Nationale de France. And there is a water clock, and the Cecibios device is here. You can see the half sphere, which is the float. Very beautiful, yeah? In China, another device was used, which is more like a passive feedback. You want to have a flow rate which is constant, and the possibility is to have many tanks. It turns out that in the last tank, the flow rate remains almost constant, since it solves the solution. It's like a passive feedback. You design the system so that it's already stable. And here's a picture. And there is also the famous Zhejiang irrigation system, DIS, which is an example also of passive feedback. Here's a picture that I have taken in 2024, and maybe a bigger picture that you can get on the web. And the goals of this DIS device are the following. First, you want to regulate the flow of the river going to Chengdu. Then you want to take care of the problem of sediments, which can increase. And also, the third goal is to get some automatic control of irrigation water. And One of the devices is a famous fish mouse levy. So it's a flow splitter which divides the flow in two parts. The inner river, which is used for irrigation and which is going to Chengdu, and the outer river, which is used for fluid discharge. And how is it working? During the dry season, around 60% of the river, which is going to the flow splitter, is going to Chengdu. And when there is some kind of self-regulation, because when this is a fluid season, the ratio reverses because the velocity is increasing, the centrifugal forces also are increasing, and then there is maybe like 40% of the water which are going to the inner river. Here's some map, and here's a picture that I have taken also in 2024. At the industrial level, the most famous regulator, the first famous regulator, is due to James Watt, and he applied it to the steam engine. James Watt didn't invent the steam engine. It was invented in France by Papin and in England by Newcomen. You see, there is always a competition between France and England at that time. Yeah. But James Watt improved a lot the steam engine by two patterns. The first one is a separate condensation chamber, which improves a lot the efficiency of the steam engine. And the second one is a double action. Instead of using the atmospheric pressure to push down the piston, he used the steam. And then the steam engine is much more powerful. But what is interesting for us is adaptation of the steam to the steam engine of a regulator which was used in windmills. And here's a picture that you can, this is a machine, steam engine, that you can see in the museum, British Museum in London, the Science Museum in London, and the regulator is here. Let me explain you how is it working. So this is a drawing due to Watt. So you have two balls which are turning around the vertical at a speed of rotation which is proportional to the speed of rotation of the steam engine. And what you want to regulate is the speed of rotation of the steam engine. Assume that for some moment, the load torque, which is applied to the steam engine, is increasing. Then the centrifugal forces are going to decrease, and the two balls are going to fly down. And then, thanks to linkage, there will be more steam going to the steam engine. And conversely, if the torque is decreasing, the speed is increasing, the ball flies up, and thanks to the linkage, there will be less steam going to the steam engine. So with this device, you may hope to get a constant speed of rotation. This is a diagram that you can see in automatic control, very useful. There is a Y, which is the output, the measurement, which is the speed of rotation of the steam engine. And it's going to act, and you will get a control U from this measurement, which allows you to get some kind of loop, which is going to stabilize the full system. That is, even if there is a perturbation, then what you want to have is still okay. Let me show you this on a movie. This is a clip movie. The movie is by Edgar Rice. It's 2013. It's about a time, this is the 19th century, about the 19th century. At that time, Germany was very poor, and many German people go to Brazil to have a better life. And here there are two German people who go to Brazil, and they construct a steam engine. Let me show you this. So they are a little nervous, yes, you see. They are anxious, and they put some effort to get more steam. It sounds to work better and better. The speed of rotation is increasing. This is a very good news. So they are very happy, yes. They are very happy. they want to share their happiness with a colleague like we do in science. And it is like in science, the colleague does not fully understand why they are so excited, yes? The colleague does not see that, yeah? And in some other room, people is working on the different, some person is working on a different subject. And finally, the speed is increasing too much. And this is a disaster. The machine just collapses. And when it happens, when you write an article, sometimes there is something which is not working, yes. There is a mistake that you find when the paper is almost finished. You see there is something which is still need to be fixed. And sometimes the idea is to look at some books, and this is what they are doing, and they see the watt regulator. They implement the watt regulator, and now everything is working very well. They are very happy. You see the watt regulator on the top. It's an excellent movie, yeah, for the subject. They are very happy. You see the young guy has changed. It's often the case also in science. The young guy is moving, the old guy is staying at the same place. Léon Foucault. Léon Foucault is a great inventor and outstanding inventor, I should say. He's very famous for the pendulum. He used the pendulum to show the rotation of the Earth. You can see such a pendulum at the Panthéon in France. And Arago wrote this very nice sentence, Foucault saw the rotation of the Earth in his cellar. He measured also the speed of light. He constructed gyro, which was also good enough to show the rotation of the Earth. And using gyro, he constructed a gyro compass, which allows you to give the geographic north, which is very useful for ships, which are made with metal. And he invented a lot of regulators, and I'm going to show you one of his regulators. This is for the arc lamp. In the 19th century, in order to produce light, one of the methods was to use, you have two electrodes. There is a little gap between the two electrodes, and you put some voltage. And if the gap is good, there is a very bright light which appears. That was a very good light. But it turns out that the light comes from the burning of the electrode. So if you do nothing, the gap between the two electrodes is going to increase, and then after there will be no more light. So you need to regulate the gap between the two electrodes. The gap should be almost constant. And the measurement, for the measurement, you use the intensity current. The intensity current gives you almost what is the gap between the two electrodes. So he constructed the first controllers to stabilize this gap, but he was not happy because an Englishman, always there is this competition, has already patented a similar device. But later on, he improved a lot the device by using two motors. One is to bring the two carbon rods closer, and the other one to separate them. It turns out that with these two motors, the regulation was much better, and it was a great commercial success. Elmer Sperry, this is the American guy. He used gyros for many stabilization issues. The first use was for cars, but it was not so successful. And then he used it for roll, to regulate the roll, to get the roll of the ship almost close to zero. And also he used this idea of gyro compass to build gyros compass, which can be used on ships. That was very successful, this. And then the last thing is, using the gyro again, he can measure the three angles, the three attitude angles of some airplane. And knowing these three angles, he can apply a control to stabilize the airplane. This is the first automatic pilot. Here is for the roll of the ship. There is a small gyro to measure on the left to measure the roll. And there is this big gyro, which is turning around some axis at a very large speed. And when you change the axis of rotation, like this, like indicated with the blue arrow, you get a very strong torque, which is given by the red arrow. So you see measurement, action, and then he stabilizes the ship. Another movie. This is Elmer Sperry. He likes very much gyros. And now there is the gyro compass. And now we are going to move to the ship, the stabilization of the ship. And this is a big gyro. You see the weight is around 3 tons. It's very large. And then with this, he succeeded to stabilize, to have a roll of the ship almost equal to 0. Very impressive, yes? Now, this is the gyro which is used to measure the 3 attitude angles of the aircraft. And another movie, this is some kind of the movie, you can see it as some advertising about the Sperry Firm Company. For us, it's like it's going to start with, you see, when we speak, and we give a conference, usually we start with, by presenting what are doing our colleagues, yes? And then you move to what we are doing. So this is the beginning of the airplanes. So the colleagues, you start with the colleagues, yes? So the colleagues, very original ideas, yes, but not working so well. Yeah. But still, it's very fascinating, yes. But very few good results, yes. This is the colleagues, yes. Now is coming Elmer Sperry, and you see him here. He's on the left, and this is the 2 sons of Elmer Sperry. And now you see everything is working well thanks to the autopilot. And in 1994, there was a competition on safecraft security, and there was this airplane from the Elmer Sperry Company. A man was walking on the wing, but still, thanks to the autopilot, the wing remained almost horizontal. Very good, yeah? Now we move to historical studies. I would like to show you 2, the first by Maxwell and the second by Lyapunov. The first by Maxwell. Maxwell, of course, is an outstanding physicist, and maybe the first paper he wrote, which is interesting for us, is his paper on the stability of the motion of Saturn rings. It was observed by astronomers as there was these rings around the Saturn, and the question was what was the composition of the rings. And he proved in this famous paper that it could not be a finite collection of rigid annulus. Because, why? Because it is not stable. It is not stable, and you cannot observe equilibria which are not stable. And he suggests that maybe the annuli are made of different blocks of different size, and this is some artist's view, and this was confirmed later on, and the blocks are essentially made of water ice. Of course, he is very famous for the theory of gases and also the Maxwell equation on electricity and magnetism. But what is interesting for us is his paper 1868 on governors. He is going to study the problem of stability of governors. And he has 2 key ideas. The first one is a linearization idea, which is an idea which is now used in many situations in many mathematical papers. And then he also gets some condition for the stability. Let me show you how it is working on the Watt regulator. So this is the regulator that he studies, the Fleming-Jenkins, but I'm not going to speak too much on this regulator. I prefer to use the Watt regulator. So first, the idea is to write the equation. You write the equation, so you introduce some notation. L is the length of the rod, m is the mass of the ball, theta is the angle of the rod with the vertical, phi is the angular velocity, is the angle of rotation with respect to the vertical axis. And what is interesting for us is d phi over dt, which I'm going to denote phi dot, which is the angular velocity, which is proportional to the angular velocity of the steam engine. This is what you want to regulate. So you write the equation, this is the first step, and you get 3 equations which are given here. The first one is just theta dot equal theta dot. Dot means the derivative with respect to time. And the 2 other equations are Newton's law. And what is interesting for us is C. Capital C is some friction term. And the other term which are interesting for us is gamma R, which is the load torque applied to the steam engine. And gamma 0 and K that you can choose, gamma 0 and K, you can choose them. This is the linkage. And then first you want to have the good equilibrium. So you write x1 dot equals 0, x2 dot equals 0, x3 dot equals 0, and you get this equilibrium, x1 bar, x2 bar, x3 bar, x3 bar. And what is important is that you get the equation for. Omega is the speed of rotation that you want to achieve. So you have a link between the load torque and the linkage. And if you have this link, then the speed of rotation for the equilibrium is a good speed of rotation. Now, you want to study the stability. You have the good equilibrium. Next step is the stability. So he first does the linearization. The linearization is a key idea which is used, as I mentioned before, in many papers. You want to replace something which is non-linear by something which is linear. Of course, some linear systems are much more easier to study. So here write x1 equal x1 bar plus y1, x2 equal x2 bar plus y2, and so on. And then he does the expansion. And he gets y dot, dy over dt, is equal to ay. And you want to study the stability of this. So if you look to solution of the form m exponential zt, and it turns out that you have a solution of this y dot equal ay with m which is not 0, if and only if z is the root of the polynomial given by 2. And of course, in order to have the convergence to 0 of exponential zt, it is necessary and sufficient to have the real part of z which is less or equal than 0. So you need to understand under which condition this polynomial of degree 3 have all its roots with a negative real part. And this is what he did in this paper. He gives the necessary and sufficient condition for the polynomial p of degree 3 in order that all the roots have a negative real part. And you see the condition is rather simple. It's a polynomial inequality, polynomial equal, while to compute the roots of the polynomial of degree 3 is already complicated, yes. And in his paper, so if you apply it to the Watt regulator, you get these 2 conditions, 2. So you need to have some friction, so you may add some dashpot. And for example, it's better to have the mass of the ball not too large. And his paper is study other regulator, and for this other regulator, the polynomial is of much larger degree. He gives an example of a regulator where the polynomial is of degree 5. And we know that for the degree 5, we cannot compute the root, but still it is possible to find a necessary and sufficient condition in such a way that all the root of a given polynomial of any degree have all the real part which is strictly negative. This was made by Ruth et Coron. But of course, you see, there is a French guy, Chalermite, who did it before, yes. Now we move to Lyapunov. Lyapunov, he did an outstanding thesis in 1892. In this thesis, there is 3 key points. First, he gives a good definition. Then he gives 2 theorems. You see, in mathematics, usually we speak more about theorems, but you cannot do any theorems if you do not have the good definition. Giving a good definition is very important in mathematics. So he gives a definition of asymptotic stability that we are going to use later on. Of course, there were previous definitions given by great mathematicians and mechanicians, Lagrange, Laplace, and Dirichlet, which are interesting for the subjects that they study, but which are not the good one for us. The good one for us is 2 properties. The first one is stability. So you have the blue point, which is an equilibrium. So you have a dynamical system, dot x is equal to capital X of x. So the blue point is a 0 of capital X. So the first notion is stability. So it says like this: if you have a ball, center at the blue point, this is the red ball, then you have another ball, which is the blue one, such that if you start in the blue one, so this is the initial data which is in green, then you remain always in the red ball. This is the stability. As t is increasing, you are always in the red ball. And the second property, which called attractor or attractivity, is this property. You can find a ball center at the blue point, the equilibrium point, such that if you start at this equilibrium point, then you converge as t goes to infinity to the blue point. And the 2 properties are different. Of course, stability does not imply attractor, just take capital X equals 0. But attractor does not imply stability. And this is the 2 properties together which give you the good notion of asymptotic stability. So this is the definition given by Lyapunov. The point is asymptotically stable if and only if it is both stable and attractor. And we say that it is unstable if it is not stable. And now the 2 theorems given by Lyapunov in his thesis. The first one is the first Lyapunov theorem, which gives you an almost necessary and sufficient condition, relying on doing linearization. So you have this matrix X prime of Xe, and he proves that if X prime of Xe has an eigenvalue which has all the real part strictly negative, then you have asymptotic stability. And if one of the eigenvalue has a positive real part, then it is unstable. You see, this is something that you can see already in the paper by Maxwell. He says this condition is mathematically equivalent. The condition is asymptotic stability, even if he does not define what is asymptotic stability. This is often the case. In physics, they have very good intuition, and mathematicians try to follow the physics. No, it's not exactly this. Of course, we go further than, because we give the definition, a good definition, and then we can get some theorem. So he wrote already in this paper 1868, this condition is mathematically equivalent, this is a condition of asymptotic stability, to the condition that all the possible roots, this is the roots which are real, and all the possible parts, this is the real part, of the impossible roots, this is the roots which are not real, of a certain equation, this is the equation which gives you z, shall be negative. And the second theorem is what is called the second Lyapunov theorem, which shows that you have equivalence between asymptotic stability and the existence of a Lyapunov function. What is a Lyapunov function? It's a function capital V defined on the neighborhood of Xe, which is strictly larger than V of Xe if X is not equal to Xe, and which is decreasing. The derivative is negative as when you follow the trajectory if you do not start from Xe. And this is why, and this theorem explains why this is a good notion for us. Because you have this type of picture. The circle are the level set of the Lyapunov function. This is the set where V is constant. And the arrow is the vector field. You see, you are pointing inside. So you are converging to the blue point. But of course, there are some mistakes, there is some errors, and this is not the real picture. The real picture, there is some perturbation, and it's like this. So, but still, if you start in the large ball, the largest one, then you are going to arrive in finite time in the green ball and stay in the green ball. This is exactly what happened for the broomstick. On the top of your finger, you can start very far away from the vertical. Then you arrive close to the vertical. You do not converge to the vertical, but you stay close to the vertical. And we apply this for the regulation of rivers. So this is a long-term cooperation that I did with many people. And I want to take this opportunity to thank them, because it was a great pleasure for me to work with them. Let me show you what is the problem. So you have some rivers. This is the river La Sambre in Belgium. In Belgium, things are almost flat, yes, so it's easier, yeah? Because when there is a slope, the situation is more complicated. And between two gates, you have what is called the pool. And you see the gate is the place where we are going to act. Yeah, there are 8 gates. So here's a picture of the pool, and you see the slope is exaggerating. We are in Belgium, it's almost flat. You cannot see the slope, yes, in reality. So we want to give the equation. The first step is to give the equation. So you denote by h of tx, the height of the water at time t and position x, and v of tx is the horizontal velocity of the water at time t and position x. And you have the gates. And the equations were found by Saint-Venant. So in France, it is called Saint-Venant equation, but Saint-Venant is French, so in English it is called shallow water equation. But this is the same, yes, this is Saint-Venant equation. And this is in the paper Théorie du mouvement non permanent des eaux, avec application aux crues des rivières et à l'introduction des marées dans leur lit. It's a very beautiful paper, but what is interesting for me is the following point. You know, usually people say that after 50, game is over. The brain is not working well enough to get something really interesting. But he gets his equation when he was 74. Yeah? I am 70 almost. So it's very encouraging, yes. But maybe in the future I have to find another example which is less conservative. And so there is a 2 equations. The first one is the conservation of mass, which is, let's forget the index I of the pool, which is the partial derivative of h with respect to time plus the partial derivative with respect to x of what is called the flow rate, which is the product of h and v. And the conservation of momentum, which is the second equation, is dv over dt plus d over dx, g times h plus v squared divided by 2 is equal to 0. And the 2 equations allows you to find the solution in principle. The gates. This picture is interesting. This photo is interesting because the gate, which is on the right, is under repair. And what is the control? Is the top of the gate, which is called the lip, and you move the lip. This is the control action. So there are many types of gates. Overflow gates, where the flow is going above the gates, and underflow gates, the flow is going below the gate. And here is some gates for the river La Meuse, which is much larger, but still in Belgium. Now, some numerical simulation. So it is divided in 2 parts. The red line, there are 2 red lines. This is the equilibrium. This is the equilibrium. And this is an equilibrium which is already stable. That is, even if you do not move the gates, you are going to converge to the red line. In front of, we are not moving the gates, but on the back, you are going to move the gates depending on some measurement. And you see on the back, the convergence is much better. Yeah. And so this is something we implemented on the river La Sambre and La Meuse in Belgium. So there is a famous thing, le régiment de Sambre et Meuse, but I will not sing. But I would like to show you on a very simple partial differential equation some idea of the proof, So this is the simplest partial differential equation that we can imagine. This is the derivative of y with respect to time, plus the derivative of y with respect to x is a special variable, is equal to 0, and you have some initial data. And there is a boundary condition, where in some sense there is a feedback A. Yt0 is equal to A ytl. So, in fact, this is just a transport equation. You just, this is this, yes. You see it's moving like this. This is a conveyor belt, hot pot, very good food. Maybe Sichuan food. Maybe Hong Kong, I don't know. I think it's taken from Beijing, yeah. So you see the transport equation. I would like to show you that in this case, we can compute what is the solution. It's not complicated. You have the initial data, and if you look to the equation, you see easily that on the line of slope 1, you can, y is constant. Since you know y0 of x, you know y0 of x, y of t and x on the red line. When we know yt and x on the red line, it means that you know also ytl for t between 0 and L. And since y of t0 is equal to a ytl, you know yt0 for t between 0 and L. And then, using again the fact that y is constant on the line of slope 1, you get the value of y on the blue line. And at the end, you get the value of y on the square. X is between 0 and L, and t is between 0 and L, and you can go further and get y everywhere. And then with this, you see easily that you have asymptotic stability of the origin if and only if the absolute value of A is less than 1. Of course, for the river, you cannot do that because you cannot compute the solution. It's not possible, it's nonlinear, and there is no explicit formula. But let's try to prove that you have asymptotic stability using the Lyapunov approach. So we define the Lyapunov function, which is the integral from 0 to L y square exponential mu x dx, and mu is a parameter, positive. And you compute, first you see that v of y is strictly larger than v of 0 if y is not 0. And then you compute the derivative along time of v of y. So you have the first formula, because the derivative of y squared is, with respect to time, is y, 2 times y dy over dt. You replace dy over dt by minus dy over dx. You recognize that 2 times y dy over dx is the derivative with respect to x of y squared. You integrate by part, and you get the last formula. And then with the last formula, you see that if a squared is less than 1, you can find mu which is positive, such that the boundary term, where there is a squared minus exponential minus mu L, is less or equal than 0, and you get dv over dt is less or equal than mu times v. And you get this without computing the solution. So this is what we did for the river. Of course, for the river, it's much more complicated. In fact, you have to go to the derivative of order 2. This is Sobolev H2. So, but let me give a commercial break, yes. Okay, let's take a rest. And now we move to the offset issue. I would like to explain you why Maxwell didn't study the Watt regulator. At the time of Maxwell, the Watt regulator was very famous, while the regulator that he was studying, there is only one sample. And this is why? Because there is the offset problem for the Watt regulator. You see, we have this connection between the load torque, gamma R, and gamma 0 and k, which is a linkage. But in practice, of course, you do not really know, you have just a guess of what is the load torque. And if you do some error, then for the equilibrium, the speed of rotation is not omega, it is slightly different than omega. So there is what is called the offset. If you have an error which is constant, the equilibrium is not the good one. And the Holy Grail in the 19th century was to find a regulator with no offset. That is, a regulator for the steam engine such that what is the load torque, the equilibrium has a good velocity, speed of rotation. So this is some attempt by Foucault, so very beautiful. And one of the attempts was isochronous regulators. And the idea is this. You know, for the watt regulator, the balls are moving on a circle. Let's assume that with some linkage, the balls are not moving on a circle, but on a curve. Then you can compute the equilibrium again, and it turns out there is a miracle for a special F. If you have the F which is given by 3, then whatever is the load torque, the speed of rotation for the equilibrium is a good one. This is very beautiful, yeah? And so there is some attempt to use this idea, which is a Bryant idea. So there is this regulator where you try to have this parabola. And there is also some other idea, which was to use the repartition of mass. By taking good repartition of mass, you have the same property, which is whatever is the load torque, the speed of rotation at the equilibrium is a good one. But unfortunately, that was not working because the equilibrium are the good one, but they are unstable. This is proved by Wisniewski in 1876. He proved that for these regulators, the equilibrium is never stable. It's a good one, but it's not stable, so it's not working. And the idea to solve the problem, I'm going to explain you, this is the integral action. You have a simple control system, which is x dot is equal to u, x is a state, u is the control. You take u of x equal minus kx, where k is positive. Then you see easily that it's asymptotically stable. You can get it by the Lyapunov x squared, or you can compute the solution explicitly. You have x dot is equal to x of 0 exponential minus kt. So very good. Now assume that you have a perturbation p. So the true system is not x dot is equal to u, but it is x dot is equal to u plus p. Of course, you could say, okay, no problem, I take u equal minus p minus kx. But it's not working like that because you do not know p. So you apply the same feedback because you do not know p. And if you apply still minus kx, the closed loop system now is x dot equal minus kx plus p. And you are not converging to 0. So x is converging to p divided by k. And the idea to solve the problem is to add a new variable. So now you have the control system x dot is equal to u plus p, y dot is equal to v. The state is x and y. The control is u and v. And the perturbation, which is unknown, is p. And you choose v equal x. And u is k1x plus k2y. So the closed loop system is 4. If you compute the equilibrium, now there is a miracle. The equilibrium, for the equilibrium, x is 0. Of course, the y is not 0 for the equilibrium, but it does not matter because we are not interested in y. We are interested only in x. And if we take k1 negative and k2 negative, this is the end of the story. You have the asymptotic stability, and you are always converging to the good point, whatever is p. And so you need to have some integration, you see. So this, and this, I have only 2 slides now. So this integration was already used into in some regulators. The one studied by Maxwell, but it was also present in some other regulator due to French guys. Yes, it's Brother Ferrier, so it's a little before. Yeah? And here is a machine, and you see, and let's make a zoom. You find like the Cesibius regulator, there is a float again. You see there is some water going into the tank, and the flow rate of this water is proportional to the speed of rotation of the steam engine. While there is a faucet that you can fix in such a way that when the speed of rotation is a good one, then the level of the water remains constant. And with this, you are able to integrate the difference between the true velocity and the desired velocity, and you get something which is robust with respect to a perturbation which is constant. So we use this, in fact, also for the river La Sambre and la Meuse in Belgium, and I'm going to stop there, and thank you very much for your attention.
Thank you very much, Professor Coron. Now let's open up the floor for questions. Yes, Professor Charlotte. Oh.
Well, thank you very much. A very, very, very nice talk. I just have a very simple question about what you showed at the very beginning, the inverted pendulum.
Yeah.
So do you assume, whether mathematically or experimentally, that it's in a plane, a vertical plane, or you allow also horizontal displacement?
Yes, this is a very good question. In this experiment that I show on the Musée La Villette, they are moving in the plane. But it's possible also to have it in 3D.
So there's some kind of rotation that...
Yeah, exactly.
that is
It's
set
moving only like this.
So you can
But it's also possible to make it like this. But of course, the problem is the measurement. The measurement, you have to,
So what do you
to measure.
measure?
What do you measure? And you need to have something which is well measured. If it's not good enough. If you try to do the experiment of the broomstick, yes, you close the eyes and try to make it. It's not so easy, yes. It could be dangerous even. Because there is no measurement.
Thank you.
A very nice talk. I enjoy all the history and also some of the function we are using day to day nowadays for the like Lilopolov. You can see the asymptotic stabilization you always mention. Do you come across if I want certain stabilization within finite time or certain time and stop? Can I do that?
Yeah, very good question. Yeah, in fact, for linear system, x dot is equal to ax plus bu. I prove indeed with Prali that if the system is controllable, there is always a continuous feedback, which allows you to get stabilization in finite time. I get some problem with colleagues because they say stabilization in finite time is not realistic because, of course, there is some error. You do not really arrive in finite time. But still, I think this is very interesting because, you can put high gains, so you get strong stabilization. But high gain, there is a lot of problems if the measurements are not good. So, but with this continuous feedback, the problem does not appear anymore. So I think it's a good idea. Then there is the problem for nonlinear system. It turns out that if a system is controllable, it does not imply that you can stabilize it. But what I prove is that I can always stabilize it, a u with a u, which depends on time and x, u of t and x. And it can make it in finite time, yes. Thank you for the question.
Thank you very much.
Yeah, thank you for the very interesting talk and the very nice movie clips. When we talk about control, I have one movie about the Elon Musk's X Space. It's about the rocket landing. It's so fantastic, so impactful. So my question about for the modern science like this, is any all the mathematics for like this rocket landing is still very old or well established or something?
Yeah, this is in fact, this is a movie that I usually show also, because this is to illustrate the fact that stabilization in finite time is also interesting, because you want that it goes back, but in finite time. Yes, it's not so. It's of course, this is very related to the talk that I have given here. You need to construct some control which depends on the measurement in order to stabilize, to get that the rocket is going back on the ship. Yeah. Of course, aerospace, satellites, this is a place where there is a lot of control theory which is used. For example, I did some work when you use electronic propulsion. Electronic propulsion is a propulsion which is, the power is very small, but you can use it for a long time. So it's very good to make a transfer which can take a lot of time, maybe 1 year. And for the satellites, so you can use some mathematical theory in order to get a control which is in feedback form, which allows you to reach the targets that you want. Yeah.
Just another question. Over here, Hong Kong and also Shenzhen is doing a lot of low altitude, all these robotic and moving objects.
Yeah.
And can you comment on something like that?
No,
how they use the control system?
I didn't work on this subject, but yeah, of course, this is very interesting. There is also the idea to use artificial intelligence, reinforcement learning. It's possible with this technique to find a feedback law. I use it, in fact, for the sterilized insect technique. You have mosquitoes, and you want that the population of mosquitoes is decreasing. Then an idea is to send in the population sterilized male, because the female does not see the difference between the fertile male and the sterilized male. So if you send enough sterilized male, then the population is going to zero. But of course, it's expensive to produce sterilized male. So you want to not send too much sterilized male. And then there is some, I use some artificial intelligence in order to construct a feedback such that the number of sterilized males that you send is optimal in some sense, not too large. It's not, you have to take care of the measurement. The measurement is complicated for this type of problem. You can measure the egg, but you do not know if the egg is a good one, if it's going to give you some mosquitoes or not. So it's rather complicated. Yeah.
Hi, Professor Coron. Yeah, thanks for our last talk. I have a question about a general question. So 2 weeks ago, I have saw a LinkedIn post from one of your collaborators, Professor Hayat. They developed a large language models-based method to do the mathematical proof, such as we can use GPT to prove the lemma or theorem in mathematics. So looking in the future, I'm wondering, may you give us insights or comments on how we combine this?
In fact, Amaury Hayat is the person with whom I did the work on for the sterilized insect mosquitoes. So he's a very good, he's an excellent mathematician, and you're right, he's working on this problem to check proof in some sense, to check proof. So you see ChatGPT and Gemini, DeepSeek, I don't know why, but sometimes the result is not good at all. For example, I remember that there is some computation, and the derivative of sine 2x, ChatGPT told me that it was cosine 2x, so he forgets the 2. So it's very interesting to have a way to check a proof. Yes, there is a lot of progress on this with some programs, lean programs, I think, LEAN. So you can formalize and check a proof, yes, given by ChatGPT or Gemini. So it's a very interesting subject. Yeah, very interesting. I don't know too much on this, but Amaury Hayat give me some insight about this, as it's a very good, very interesting subject. Yeah.
Thank you.
Very nice discussions. Any other questions? All right. If no, I would like to conclude the lecture time for now. Thank you very much, Professor Coron. Please join me to thank Professor Coron again. All right, so that's the end of the lecture now. If you'd like to stay to ask some questions, feel free to do that. Otherwise, have a good evening. Thank you guys very much.